So welcome back. Last lecture, we have discussed quite in detail how maximum entropy principle derived from information theory enabled us to rediscover the static distributions of the canonical ensemble. Remember the problem, we have a Liouville's equation, which is formulated in terms of the phase space density. And at least at the beginning, we are only interested in the static distribution, the static solution of the Liouville's equation, which is the solution that obeys partial derivative of the phase space density as a function of time go equal to 0. So the right-hand side of the Liouville's equation, if you want, equal to 0. Because this is what we identified as the relevant stochastic descriptor for equilibrium and thermodynamics. Equilibrium distributive properties and thermodynamics. Correct? Do you remember that? So our question is, can we infer not the entire time evolution of the system, not the entire dynamics of the phase space distribution, but only its asymptotic stationary solution? Of course, we will need to do more than that eventually, if we are interested in dynamics. But let's say thermodynamics is the minimum amount of information that we want if you want to describe a complex system. So in order to get thermodynamics right, we need the distribution, and the distribution is the stationary solution, is the solution of the stationary Liouville's equation, at least in this Hamiltonian phase space density standpoint of statistical physics. And the way we achieved this result was to define a functional which involved an integration over the phase space variable of the density that we are aiming for times the logarithm of the density with some k in front, plus negative k. And this is the conventional entropy, right? Plus constraints. And specifically, if we're interested in the canonical distribution, there were two constraints we introduced. One constraint was just the normalization of the stationary distribution, which is simply telling us rho is a distribution. That's all it's telling us. Why? Because if rho was negative, the logarithm would become very angry. And so rho must be positive for this to make sense. But in addition to be positive, it must be normalizable. And anything that is positive and normalizable can be interpreted as a distribution, right? So if I only allowed entropy to be maximized subject to this function, everything I would get off is the most general, the most unbiased distribution, which probably would be a uniform distribution. We already had this exercise, remember? So that's clearly not enough. We added a second constraint. I might change slightly the notation with lambda prime or beta prime, it doesn't really matter, the name of the Lagrange multiplier that I put here. But the important thing is what comes after, and what comes after is the integral over phase space of the phase space density and the Hamiltonian, which basically defines the phase space average energy, set equal to its pre-established average energy. which is our fixed value we want to adjust to. Now, we demonstrated that functional differentiation with respect to rho, which we had to define in the last lecture, but functional differentiation with respect to the rho will yield naturally the structure e to the negative constant time Hamiltonian. How so? Well, first of all, when you act with functional differentiation with respect to this, basically what you get is that the distribution is the exponent of some function, right? And this is completely logical if you think about it, because the exponent is a positive definite function. So if you only maximize with respect to this, you get positive definite quantities, right? The condition here basically is nearly irrelevant. It just introduces this constant into the expression of the exponent, if you go back to your notes, which basically tells you have to normalize these at the end of the day. Remember that? But what is interesting is what happens at this level. So, although you probably cannot read very well because there's a computer in between, maybe now you can. It's an integral of the phase-phase variable, d gamma, rho, the distribution, and the Hamiltonian. So both rho and the Hamiltonian are functions of gamma, which I did not explicitly denote here for the sake of space. And negative, the average value of the energy, which is the parameter I want to keep as fixed. Now, when a function will differentiate with respect to a rho, I drop out the factor h. Right? Remember that? But since from the previous part we know that whatever we get into the exponent because of this function differentiation with respect to this part, remember? What we mathematically derive, I'm just resketching the derivation, I'm not giving a new argument, I'm just going fast on something you can see in previous lecture. The result is rho will be proportional to negative constants times energy at the exponent. So e to the negative constant time Hamiltonian. So there we go, that we got to the expression rho proportional to negative constant times Hamiltonian of gamma, which is already 99% of the work done for getting the canonical distribution right, correct? Now, of course, we were left to determining the normalization, which enter, if you want, here, and the value alpha. The normalization n is trivial, it's just the integral of the distribution over the entire support. The parameter alpha was fixed by imposing thermodynamic consistency. In other words, by requiring that the resulting free energy that you get from this was in fact the free energy of thermodynamics. And for this to happen, this k that enters in this functional was supposed to be the Boltzmann k, and this was really the entropy. And this alpha was supposed to be the inverse of the thermal energy, 1 over kT, which is sometimes called beta in the statistical mechanics literature. Remember that? So the ingredients here were maximum entropy, and for fixing the parameters, thermodynamic consistency. Okay? Okay, so that's more or less where we arrived last lecture. We want to pick it up from here, okay? And in order to do so, I want to remind you guys that we are interested ultimately in applications to macromolecular systems, and more specifically, at least as far as I'm concerned, to macromolecular systems of biological interest. And biology is pressure sensitive. In other words, if you try to survive in the bottom of the Marianne Deep, you don't, right? So it's clearly, along with controlling the temperature, which is an important thermodynamical coordinate for biological systems, if I increase your temperature by 40 degrees, you clearly die, right? And we need also to control temperature. Sorry, pressure. So we now need to address the question, what is the most general distribution consistent with having fixed energy and fixed average energy, which is, we discussed, as a matter of fact, equivalent as fixing the temperature. So let's say fixed temperature and fixed pressure, right? Now, in pursuing these questions, in tackling this question and some of the next questions, I decided to take one particular approach in this course. Since we have a lot of material to cover, I normally, whenever we happen to have in the course one topic and then a closely related topic that basically is a continuation of the previous topic with a little bit of changes, I do the first topic thoroughly and the second topic more like sketching, right? Because if I do everything the same level of thoroughness, I don't arrive at the end of the course covering enough material. So in the following derivation, it's basically the same as the previous. I will emphasize the difference and be a little bit more quantitative rather than doing all the calculations. And of course, I expect the same from you in the exam. Okay. Anyway, in the notes that I'm updating, and I'm going to deliver you on a monthly basis, roughly, you see all the derivations in case you're interested. Okay? Okay, so now the big point that I want to make is that if I want to keep energy, average energy, and pressure constant, I must be ready to give up volume. Because that's exactly how an isobar transformation is performed in classical thermodynamics. Remember your first year where you were doing, you had your simple systems, you had your piston with a gas inside, and then, sorry, this was the piston, here was the gas, and there was a pressure outside, and then you were like building PV, or actually it was PV transformations. And then in order to keep pressure constant while you, for example, while you were heating the system, you were giving up being volume constants. Because pressure, volume, and temperature are fixed by the equation of state, which for ideal gas is simply PV equal RT. Of course, this is only true for ideal gases, not for any system. But what is in general true is that an equation of state linking this thermodynamic variable. So if you want to keep pressure and temperature constant, you need to adjust V. Okay? So I make this premise to say that in order to achieve our goal, that is to define a distribution, and phase-space distribution that preserves pressure, we need to enlarge our phase-space variable sorry, phase space distribution and phase space to an extended space where now the density distribution depends on both gamma and V. So in other words, you want to imagine copies of these systems, each of which with its own phase space, each of which compressed at a different volume. To be practical, molecular simulations, you have your solute molecule, say a protein, your solvent molecule, say your number of atoms of water molecules. Now, if you put the same number of water molecules, but you decrease by 50% the size of your simulation box, clearly the density will go up, and and if you keep the same temperature, the pressure will go up. Okay? Okay, so the idea now is to look for a new distribution which will depend parametrically on volume. You might think about this as a parametric dependence, while the gamma being the real variables, but it is more or less a nomenclature thing. The distribution depends on all of these variables. I like to distinguish between them because the phase space is a truly dynamical concept, and the Hamiltonian really describes evolution in phase space. But this might come with a parametric dependence on volume. Okay? So now the idea is to do exactly the same as we did last lecture, to write down an entropy of rho. But now this entropy will contain an additional integral over the volume. Integral dv, integral d phase space coordinate, rho of gamma v log rho of gamma v. Note that I have now integrated over the volume as well. So from the point of view of rho, v is not really a parameter, it is really a variable because the normalization and the definition of entropy contains v. Okay, in the back of our mind, gamma contains the active degrees of freedom and v is the box. So in the back of our mind, we see a distinction between these two sets of coordinates. But as far as rho is concerned, they're democratized down to the same level. Now, instead of adding the Lagrange multipliers, let me add the constraints directly that we want to add on top of this. And then you can easily translate that into Lagrange multiplier, right? Well, the first constraint is, of course, the good old normalizability. The integral of the rho d gamma dv of rho of gamma v must be equal to 1. The second constraint is we still want a temperature. So we still want to fix the average value of the Hamiltonian. Now the Hamiltonian itself will depend on the volume. Why? Well, the simplest way to think why the Hamiltonian depends on the volume is to imagine to do a simulation. If I actually do a simulation, I put my particles in a box, and the value of the Hamiltonian will depend on the size of the box. Now the box might have periodic boundary conditions, as we will see later on, and there might be other ways to treat in electrostatics which implicitly know about the volume, and there are many technicalities we might worry about. But as a matter of fact, the value of the Hamiltonian depends on the volume. Think about stuffing too many molecules in a small box. Okay? For example, you might imagine confining your water molecules with a repulsive box. Now, when your molecules are, you don't do that in simulation, you actually prefer periodic boundary conditions, which means when a molecule exits from one box, enters from the other side. But this is a practical implementation. Conceptually, you might think of really putting a box which means putting a repulsive force to prevent molecules to go off a wall. Now clearly this interaction will appear in the Hamiltonian, right? You follow me? So the Hamiltonian will depend explicitly on volume. Okay? So the next constraint is the integral over the volume, integral over the phase space of rho of gamma v, h of gamma v equals to the whatever average value I want to control. Okay? But now I have the third constraint. Now, to determine what is the third constraint, I want to revisit what we did. When we imposed the Lagrange multiplier, we did not impose the Lagrange multiplier directly on the thermodynamic coordinate we wanted to fix. We imposed it on the conjugate variable. What does that mean? We wanted to keep temperature fixed. Then we were ready to allow for fluctuations of energy, right? We want to keep energy fixed, temperature will fluctuate, okay, around an average value. So when we were doing the microcanonical, we were keeping energy fixed. When we were doing the canonical, we were allowing energy fluctuation and we were fixing the average values of the fluctuations of energy, right? So now we want to keep pressure fixed, and the conjugate value to pressure, the conjugate variable to pressure is volume. We want to keep pressure fixed, we want to allow volume variations, right? So this is not to say that the third constraint is integral dV, integral of d gamma, rho of gamma v times v average volume equals to whatever average volume we have. Very well. So now we basically have it all. Because you see, now the derivation of what is this going to be in terms of stationary distribution can be almost directly inferred from the derivation we had before about the canonical ensemble. From the functional differentiation of the entropy itself, we get the fact that rho is the exponent of whatever terms will come from functionally differentiating the constraint. Remember? So this will only tell me, hey, put the normalization factor in front. And these two will say, put a minus comes from here, put a minus exponent, minus constant time Hamiltonian, and here we say put minus constant times volume, right? For the very same reason. You follow me, guys and girls? Okay. So, what do I learn? I learned that my new distribution of gamma and v will be constant, which I will still write as n, which ultimately will be my partition function, remember? Because the normalization is the partition function, which has a thermodynamical interpretation. Is the negative exponent of the free energy. times e to negative a first constant I will call beta for obvious reasons times h, and another constant we call gamma times v. And now I'm left with fixing these coefficients. And again, you fix these coefficients by imposing thermodynamic consistency with what we want these to represent thermodynamically. Okay? And here is where I'm going a little bit sketchy. If you impose thermodynamic consistency, you get the beta is actually 1 over kT, as you already knew. But from thermodynamics consistency, you get gamma is equal to P, your reference pressure. So actually, what I can do, I can replace this with P. And the integral of this over the phase space is the partition function 1 over n. Okay? And so just to make sure, if I do this, it turns out that 1 over n, which I also call delta, which depends on pressure, volume, and temperature, is the integral of d gamma, d volume, of e to the negative Hamiltonian minus PV, is called the isothermal isobaric partition function. Now I'm skipping some subtleties here you find in the notes, but this is the kind of degree of detail I really aiming for to understand how simulations work. Because when you will do simulations, you will have to adopt a combination of isothermal isovolume or isochor steps and isothermal isobaric steps. And you have to have clear in your mind that you're sampling slightly different ensembles. But there is one fundamental fact of statistical physics which follows basically for central limit theorem. A large number of considerations that in the thermodynamic limit, all these statistical ensembles are equivalent. In the thermodynamic limit, provided I adjust the energy of the microcanonical to match the average energy of the canonical, I get the same averages whether I'm using the canonical or macrocanonical ensembles. And provided I match the average value of the volume to that corresponds to a given fixed value of pressure of the isobaric isothermal, I can use both to get the same averages. Remember this fundamental fact of statistical physics, called the equivalence of your ensembles. There's a very brief and concise physics-based discussion of this in the first introduction of the statistical physics book in the Landau series of books that was written by Pitajewski, who I had the luck to be colleague of when I was in Trento. He was still teaching and working in Trento until 5 years ago. He told a lot of very funny and interesting stories about Landau, which maybe one day I'll tell you. Anyway, he was last student of Landau. One of his most respected students. Okay, very nice. We now have theory under control. And as a theoretical physicist, I could say, okay, problem solved, let's go home. But of course I would be wrong, because theory without anything to solve the theory and to use the theory is useless, right? So now the real question is, can we develop algorithms and practical ways to sample these ensembles? So now we move from conceptual to practical, right? So we have established what we want. We want this distribution. But now we want a way to sample from this distribution. And I want to insist on this concept. Although it might be very trivial for some of you, let's go back to what it means for a moment to sample from distribution. This, again, this notion is very familiar, I hope, for you, but it's worthwhile insisting on it, just one tiny bit. In equilibrium thermodynamics, what we are interested in are equilibrium averages. You take an observable, and if you are at equilibrium, there is no time. What we want is the phase space or extended phase space if you're talking about the isobaric ensemble. But let's talk about the canonical ensemble for sake of simplicity, and only imagine phase space variables with the mutual gentleman's understanding that if you're dealing with slightly more complex ensembles, this is an extended phase space coordinate that includes, for example, volume. Okay? Then we have rho of gamma, and then my observable, which must be a function of the dynamical variables of the system, right? This is your goal. Why is this your goal? Well, for once, because this is something you can measure. And as a theorist, this is something you can predict. And this is what you want to do as a theorist. Predict things that experimentalists can measure. Okay? Okay, so in principle, one has a nice expression. If I gave you the analytic expression for this, for example, for the canonical ensemble, this is 1 over z e to the negative beta the Hamiltonian as a function of gamma. Well, I have reduced my problem to computing an integral. So, in many cases, this is called reducing to quadrature a problem. When you have a complex problem, a differential equation, and you're able to express the solution as an integral, in most cases, you're super happy. Because all you have to do is to do integrals, and computers are fairly good in doing integrals. Let me stop it for a moment there and give you an example of one situation where we are super happy to arrive to a point where we can compute an integral. Okay? Say we want to solve electrostatics. Electrostatics is solving the Laplace equation for some charge distribution R. Right? Remember that? Now, this has nothing to do with statistical physics. And this rho has nothing to do with the phase space variable. This is the electric charge density. Now you probably remember from your previous education that you can actually rewrite this. You go to Fourier space, and then you anti-Fourier space back, and the result is that phi of r is equal to integral into y, rho of y, 4 pi epsilon naught, r minus y. Remember the Coulomb interaction, which first year, probably in high school, you consider this, say, okay, electrostatics is linear, so I break the contribution of the electric field produced by each little bit of volume inside my charge density, and this is the Coulomb potential for each, and I integrate over all the volumes in the source of the electric field. Now, when you are more advanced, you do that with the Green's function method. I hope you have done that. Never mind if you haven't. But once you have this expression, this is a three-dimensional integral, not the simplest integral to glue, but with modern computer, you can certainly do for whatever charge distribution you want. And it's fantastic. You're done. You give me the charge distribution, and I give you the electric field literally everywhere. This is going from science to engineering. Right? Well, this is what I want. This is an integral. This is an integral. Why I'm not happy with this? I'm claiming that this strategy, here we are not anywhere close to making it. Why? Conceptually, they're very similar, right? My answer is an integral of things I know. What is the difference between these two? I know the free spaces, dq1, dq2, dq3, dq4, dp1, dp2, dp3, dp4.
I mean that I might be able to sample.
What does it mean to be able to sample? Because what do I do for doing this? For example, I break the space in cells, because that's the Riemann's definition of volume integral, right? I compute the integrand in each of the cells, and I sum over, right? Most of the cells will be zero because, well, not exactly zero. The rho in most of the cells will be zero if rho is limited, but I might still get a finite result because of this in a point R where rho is zero, which tells me that the rho is a source of an electric field that can be extending further. But nevertheless, this is a three-dimensional integral. This is a 7-dimensional integral. So now, we can teach a computer to break a one-dimensional function into a grid. No big problem. Any laptop, even a cell phone, can do it in no time. One-dimensional integration, done. Two-dimensional integration, okay. Three-dimensional integration, I'm talking about exhaustively breaking this into a grid. Well, yes, but it goes exponentially with the number of dimensions, right? Because now for each x and y, you have z cells to compute. Now, here we're talking about 1 million dimensions. Well, say, maybe 1,000 dimensions if I'm using water implicitly. Forget about doing that on a computer. Not to mention analytically, of course. Unless you have an ideal gas. Why do I want an ideal gas? Well, in ideal gas, the phase space distribution factorizes into a product of one-body distributions. And then all of a sudden the kinetic energy goes away, you remember, because this is kinetics times potential energy. The kinetic is just a Gaussian, you can do it. So you basically now, if you have just that, basically you can do n Gaussians, integrations, and you're done. Okay? But if this is not an n one-body distributions, but is a one n-body distribution, this is an undoable integral for any computer you can think of. Okay? And here comes the idea of sampling. Which is the basis of all stochastic approaches. I'm sure you have seen some of them. Now the idea is, rather than keeping each point in space with equal weight and sum over this product, I sample points from this distribution, which means that now I have a collection of phase space points which are not uniformly distributed on a grid, n-dimensional grid, but they are sampled randomly from the row distribution. So the probability of having my point is going to be rho of gamma. So there are some notations that people use. Some people use this. I say I take n values, gamma I, different points in phase space. I'm going to schematically, let me represent phase space in 2 dimensions. Rather than breaking phase space in small boxes and summing over all of them, in each of them, computing this product, and then sum everything together. This is the exhaustive approach we have just discarded. You follow me? I don't take this view. I sample some point. And what does it mean, some points? That the points that I extract don't come with equal probability. I extract points more frequently if they are near the maxima of the row, and less frequently if they're near the minimum of row. In other words, I sample this point with a probability rho of gamma. Now, some people use the wiggle to say that these are distributed according to this. Some people use the set belonging to denote sampling. So they say this belongs to this, which is kind of a abuse of notation, because of course it's not an element of a set. But the important thing is I have a way of extracting configurations whose relative probability follows my distribution rho. Okay? Now if I do that, and I take infinitely many points, a theorem called the central limit theorem you must have heard about in your education ensures that this average is equal to the arithmetic average over the value of O computed in my set of points. And again, provided that these values of gammas are not taken exhaustively through the lattice, but they are taken with a probability rho of gamma. And you have similar equation to get the statistical errors on O, which basically follows from the variance computed on this. So the average of O squared, negative average of O squared, right? If you have done experimental analysis, you know this. When you do error analysis, you assume you have picked the simplest error analysis, the one that leads to chi-square, is one in which you assume you have picked your experimental measurements from Gaussian distributions around the exact value, right? And then you maximize the likelihood, and then we give it a chi-square. That's essentially the same statistics here. Okay? Sorry? We have a 1 over n here, of course. Sorry. It's an arithmetic averages. Thank you. So, going back to the problem we began with, we now have two distributions, the Boltzmann and the isothermic isobor. So, they sample two different ensembles. The NVT ensemble, where n is the number of particles, fixed. T is the temperature, fixed. volume fixed, and the NPT ensemble, number of particles fixed, pressure fixed, temperature fixed. Okay? So we want to sample these two ensembles, which means we want to generate configurations whose relative weight is precisely the corresponding equilibrium density that solves the stationary Liouville's equation. In other words, the two functions that I defined, this and the one where you omit the v part. Okay? You with me? There are many ways to do that. You might be familiar with Monte Carlo methods. Have you heard about that? Metropolis Monte Carlo methods. We will not deal with them now. But in Metropolis Monte Carlo, you start from one configuration, you make a trial move by perturbing this configuration. In other words, you pick another configuration in phase space. And then you have a criterion called the Metropolis criterion, whether you want to accept or reject your move. If you accept your move, your chain is added a new configuration. And if you reject the move, your chain is added a copy of the previous configuration. And you keep on doing this. Now at the beginning you will be out of equilibrium, meaning that at the beginning your chains of configuration will depend on your initial choice. But if you take this out, at some point you perform an average over all these chains. This will basically, what the Metropolis would say that the relative probability of the distributions that you generate this way will be, if the Metropolis acceptance and rejection criterion is done correctly, be distributed according to the right probability. Molecular configurations, macromolecules are not the ideal systems for Monte Carlo moves. Well, not entirely true. You have the correct statement would be to do this with macromolecules, you have to be very, 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 very careful. Why? What is the typical move you would guess if you want to study a particle in a potential? Perturb the position of the particle, or perturb the velocities of the particle. Correct? Now, if you have a macromolecule, if you just pick one atom and you change the coordinates, you immediately stretch the covalent bond, making it very angry. Or you have two atoms overlapping, making it even more angry because R to the 12, remember, the repulsive curve, gets angry very fast, almost like my wife. So you don't want to get my wife upset, and you don't want to get the van der Waals term equally upset. It'd be interesting to do the competition. So what happens? Since the acceptance-rejection criterion is involving energy, typically going too much high of energy will give you exponentially low probability of acceptance. If you do a naive Monte Carlo for macromolecules, most of the time you get rejection, which means that you will generate Metropolis chains with huge correlations between the same configuration over and 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 over. So before you can see a statistical variability that grants the fact that you have enough configurations, you must generate an outrageously long Markov chain, and before you're done, you're run out of computer time. Okay. Now, there are smart ways to engineer the moves so that you don't get some of these constraints unhappy. For instance, there are ways called crankshaft moves for moving only, for generating moves that preserves the length of the bonds. Now, these moves will not get the bond stretching or bond angle depending how you do your moves, upset. Great improvement. But you're still going to make the van der Waals collision upset. Now, since proteins and many macromolecules are compact objects, collapsed polymers, these moves become exponentially ineffective in the compact phase. They might be okay for swollen polymers, say intrinsically disordered polymer in highly denaturating conditions, because the chance of running into clashes might be relatively low. Okay? Am I talking a language you follow more or less? Have you done ever your Monte Carlo calculation in your life? So you know what I'm talking about. So, fine. So if I cannot use detailed balance and Monte Carlo and Metropolis to sample configurations, am I lost? You see, the idea is to use the equivalency of the ergodic assumptions. In other words, remember what the ergodic assumption or the ergodic hypothesis says. The ergodic hypothesis says that if there is an equilibrium distribution and my system can populate the entire phase space, eventually long enough time series will be equal to long enough, to phase space averages. Okay? But what is a time series? I want you to think about this. So let's make two strategies, Monte Carlo and what I will call molecular dynamics, which means solve Newton's equations or Hamilton's equations for your Hamiltonian in time. Okay? Okay. In Monte Carlo, I start from a seed configuration and I generate the next by a Monte Carlo move, which is a stochastic process in which I throw a dice and I perturb my configurations, and then I keep on doing this. Now, by the very nature of Monte Carlo moves and Metropolis acceptance rejection criterion, some of these gamma will be the same. And precisely those where I have rejected the move. Say, for example, that from gamma 1 to gamma 2, I have rejected my move. Right? Then this will be gamma 0, gamma 1, gamma 2 equals gamma 1, and then gamma 3, which is different. Maybe from here to here I've accepted it. Okay? Then I take a very, very, very long string of this, and I use the central limit theorem, and I get by construction, by central limit theorem, and by Monte Carlo theory, I get that the last part of this chain will be distributed according to the right distribution. But if it's infinitely long, whatever happened in the beginning has zero statistical weight. So, right, because it's just the beginning of an infinite long string. Just for conceptual reasons, I can average over all of them. The fact that I don't necessarily have to average over all of them is a practical way to reduce the dependency when you do calculations. But conceptually, I'm dealing with infinitely long, so I don't have to worry. Okay? You follow me? So basically what I do, I generate a trajectory. You can think about this as a trajectory in phase space, right? Because in phase space, I started from here. I've accepted my first move. I've rejected the second move, so I've done this. I've accepted the third move, and so on and so forth. Now, let's talk about molecular dynamics. In molecular dynamics, I still start from a point in phase space. I've got to start from somewhere, right? You with me? But now I evolve according to Hamilton's equation. Or if you want, equations of motions of the system. Newton's equation, ultimately, for most systems. Okay? And I get a new configuration. That's t plus delta t, right? And we already discussed how to do that for the microcanonical ensemble. Remember that with the leapfrog algorithm? And I keep on doing this. Now, the real difference is that none of this configuration is exactly the same. Because I will always generate, unless I'm in the deep minimum of the Hamiltonian and I have zero velocity, in which case I will stay there forever, every other situation will drop me somewhere, right? So I will generate a trajectory. So both with Monte Carlo I generate a trajectory, and the central limit theorem applied to this ensemble of configurations that form this infinitely or very large chain will give me the phase space average. In molecular dynamics, I generate a time series, and the central limit theorem of this time series will generate a time average. Correct? Yes or no? But the ergodic hypothesis will tell me that I can do that equally well. That both of them are equally well good solutions to my problem of sampling equilibrium languages. Correct? So which one is best? There is no real answer, but let me just say that by definition, molecular dynamics will avoid, for instance, clashes, because when the configurations get close, repulsive forces will take care of avoiding clashes by themselves. So it would seem that molecular dynamics has a huge advantage because all of these problems of sudden rise of energy and physical rises of energy are not there, since the dynamics prevents these unphysical events to occur. You follow me? However, it is not quite so, because you have a price to pay. In order to integrate molecular dynamics, if you have steep energy variations, like if you bond stretch or if you overlap clashes, you have to take an extremely small integration time step. Because you move atoms by very little, so that the force that you start to experience start to grow gradually before your algorithm becomes unstable, right? So you get two atoms closer, they experience some van der Waals repulsion, and they smoothly get far. Now you start to see the two sides of the same coin. In Monte Carlo, if you want to keep if you want to keep finite acceptance rates, finite chances of accepting the move, you have to make very, very, very shiny moves, as opposite of bold moves where you try to move a lot configuration. So all of these configurations have to be all close to each other. If you are too brave and your system is complex, you move a lot, but you reject your move. Molecular dynamics, in order for your equations to be faithful representation of the dynamics and to be stable, most of all, you have to make small integration time steps, which ultimately lead to highly correlated configurations from step to step. So more or less, you're looking at the same problem from two different angles. However, in the end, most of equilibrium dynamics for biomolecules is currently done with molecular dynamics. I would say if you're dealing with soft matter and you look at polymers, there are good, very good polymer, say, sampling. Normally people use advanced Monte Carlo techniques. There is no fundamental way to prefer one or the other, and the reason behind this fundamental impossibility of discerning between these two options is because we have decided to believe in the ergodic hypothesis. Okay? Great. Other questions? Sure.
For example, we use Monte Carlo in order to do an average. We have to.
Sorry?
No, I was saying if we are using, for example, Monte and we want to do averages, we take configurations in the free space, we get rid of autocorrelation. Let's say I have an autocorrelation. I cut and not a certain number of configurations. I do the average, and the average is and then sorry, the central limit theorem is true. So I might do the same with molecular dynamics in the sense that I produce a time series, I recover an autocorrelation, and I cut, and then the central limit theorem will be true in the sense that I will have the same average, but I will have 1 over n, which is the number of time steps,
yes,
times the delta of the time steps, and that is
yes,
normalization factor.
right. So in other words, you're saying me, my real statistics is not the number of configurations that I've generated, but is the number of steps that I've taken divided by the autocorrelation, which means for the central limit theorem to be correct, I want my correlations to be independent, and for them to be independent, they mean they are uncorrelated. Well, this is not exactly true in the sense that the average will always be good. What will be completely wrong is, of course, it's not guaranteed to be good, of course, because if I had never moved from my configuration, it's not. But what really you're screwing off very much is your estimate of the error. If you're assuming that highly correlated configurations are Gaussianly distributed, as the central limit theorem would imply. Now, there are more sophisticated ways of dealing with correlated error estimation for correlated samples. The bootstrap technology is the simplest correction you would do, which usually takes you 80% of the way through. So there might be a way to retaining more configuration, even if they are correlated, accounting for the presence of correlation in your estimate of the error, which typically becomes larger than the error you would estimate from the same number of correlations in a Gaussian statistics. But here we're entering a little bit of technicalities that I would like to leave a little bit under the radar for the level of this course. But yes, conceptually you're right. The point that I try to make in all this digression is that throughout this course, very often, and in the literature, very often we will be using molecular dynamics to sample equilibrium, which is kind of it might sound like shooting a mosquito with a gun, because molecular dynamics really solves the entire dynamics. So in principle, it includes also the transient phase in which the rho distribution thermalizes. Remember, you have an initial rho distribution, which depends on time for some time, and then stops depending on time. And then your algorithm sort of gets rid of all of the juice, all of the interesting meat, the dynamics, and only retains the less interesting one, that is the equilibrium. So in order to get to the equilibrium, you have to do all of this non-equilibrium stuff. Now clearly, if I were able to do very bold Monte Carlo moves, I would explore configuration space much more efficiently. But my configurations would not be having any, my trajectory would not have any physical meaning. Conversely, in molecular dynamics, my trajectory does have this physical meaning of evolving in phase space. So it's really like the evolution of my distribution is supposed to happen under a Hamiltonian evolution. But at this level, at this lecture number in this course, we are not interested in that. We are interested only in the equilibrium. We will be interested in dynamics later. So there is a fundamental difference, of course, between the Monte Carlo approach and the molecular dynamic approach, is that molecular dynamics not only yields the equilibrium distribution, but in principle, if done properly, yields the entire dynamics. Protein folding, start from an unfolding ensemble of configurations, get an equilibrium population of folded and unfolded. The full glory. So, this long premise is to say, now we want to find a way to find dynamics that samples those distributions. Now, if you only integrate the leapfrog algorithm, provided that you do mistake, but in the ideal limit in which delta t is so small that I don't have to worry about any violation of energy due to the finite discretization, and computer time is not an issue. We will deal with finite computer time later on in this course. In principle, a leapfrog algorithm will sample one specific ensemble. Which ensemble? Leapfrog is, I integrate Newton's equation of motion as they are. The microcanonical ensemble, right? Okay, you might say, that's all I need, equivalence of the ensembles. I have a huge system, I integrate the microcanonical ensemble, I compute my average, I tune the energy so that the pressure, the temperature is more or less correct. I tune the number of particles in my box so that the pressure oscillates around my average value that I want. And I'm ready to pay the price to do several trial and errors until things stabilize to the values I want of pressures and temperature. And if I have so many particles that fluctuations are small, what's my problem? So from the conceptual point of view, the leapfrog algorithm is all you need because of the equivalence of the ensemble. The problem is you don't want to have, you don't want to worry about violations that occur when the number of particles is limited. And you see, if you are dealing with a protein without a solvent, for instance, this is in fact an issue because the protein may have only 100 particles, just a peptide, a few peptides, or maybe 1,000 particles. Root of 1,000 divided by 1,000, that's a typical error you make, right? It's not that small, after all. So, equivalence of the ensemble might be questionable in some systems. And there is, in addition, if you really want to do microcanonical and keep the energy fixed, leapfrog is not good enough. So that's not good anyway. But there is a way out. Now we're going to define, I will just, okay, I think I have 10 minutes, so I will not go over the entire derivation. Am I correct that I still have 10 minutes, or am I wrong again?
Yes.
I started 2:30 this time. Right. Okay, so here's the point. If I start with my Hamiltonian phase space, I do Hamilton equation, I get rho microcanonical. Right? The idea now is to start from a slightly different Hamiltonian, H prime, which depends on h, and possibly some additional variables. For a moment, let's call it S. What is S? It's one extra degree of freedom that I choose to include. What is its physical interpretation? Forget it. It's not something that exists. It's a mathematical trick. Okay? I solve Hamilton's equation. I will get the equilibrium, I will get the microcanonical distribution of this new Hamiltonian, right? But then I do an extra step. I marginalize with respect to the unphysical variable S, which I'm using into commas because it very much depends what ensemble am I doing, what kind of variables I'm adding. Now with S, I'm just saying some unphysical variable. It will happen to have this name also in the specific example we will consider soon. But for the time being, it's just some extra degrees of freedom. So if I build the Hamiltonian, listen to me. The smart thing is you invent an Hamiltonian such that if you run the dynamics and you marginalize with respect to the extra degrees of freedom, the result will be e to the negative h of gamma, your target distribution. Let's say rho target, because I have been agnostic in not telling you what S is, because I want it to be general. So let me repeat this idea again, because at the beginning it seems irrational. You have a large phase space, you make it even larger, and then you average out whatever you've added. It's like putting something in to just throw it away at the end, right? By throwing away, I mean marginalize, because if you marginalize over a variable, you're averaging out the information about the distribution of that variable. So why do I want to introduce a variable if I then average out the information about its distribution? Because by doing this, I can engineer, and I will give you the demonstration, of course. You will have to believe me. I'm just throwing down the general idea before I start doing the math. Okay? I can engineer the Hamiltonian in such a way that after I marginalize over the extra variable, I get the correct target distribution. It sounds magic. How can this possibly work? Now, if I ever have learned something doing physics professionally for 25 years, is that whenever math works, is almost never by chance. There's always a physical reason underneath it that makes it work. Talking about physics, of course. Talking about economics, of course, is a different story. So I want to make you think, you probably don't need me to make you think. What I want to say in English is, I want to suggest you reconsider what is the canonical ensemble. How is the canonical ensemble defined? Conceptually, exactly in the same way. You have your system. Energy fluctuates because your system is in contact with a heat bath. But you're not really interested in the heat bath. You're interested in the system. So what do? You include the heat bath and the system into a closed universe. But then you statistically focus on the system only, averaging out the contribution of the heat bath. Remember that? That is the conventional way of dealing with the canonical distribution, not the information theory way that we have discussed in this course, precisely because I assumed You have already seen this microcanonical construction, the Gibbs-Boltzmann way of thinking about it. Okay? But if you think about it, what have you done? Go play this movie on reverse. You started from a system you're interested in, you enlarged it by introducing new degrees of freedom, the Bath degrees of freedom, and you've averaged out the new degrees of freedom to go back to your system. The difference is, I had to use a lot of degrees of freedom to make a hit path. But sometimes, you don't need a lot of degrees of freedom to make a hit path. Like we think of it, let me give you an example. When we do freshman thermodynamics, by freshman I'm using the English-American notation that the freshman is first year, for those of you who are not familiar with this. If I do freshman thermodynamics, how do I keep an isotherm transformation? I allow the volume, the position of the piston to change. So what do? I add just one extra degrees of freedom, the position of the piston. And the dynamics of these extra degrees of freedom is sufficient to keep temperature constant, correct? So to keep temperature constant, you don't need an exponentially large number of degrees of freedom. That makes it work in nature, yes. But you can also get along with just 1 degree of freedom if engineered properly. And that's exactly what this S variable will do. It will play the role of a piston, adjusting. Actually, what this S will do will rescale times and velocities for any instantaneous variation from the average kinetic energy to be compensated immediately. So it's like if this extra degrees of freedom was a guy with a magic touch that can slow time, just a tiny little bit, so that when your kinetic energy is a little bit too fast, you just tiny little bit slow time, slow all the part, or if you want, if you want something less magic and more probably meaningful, you can slow all the particles by just a tiny little bit. But you understand, slowing down the particles and dilating time is the same thing in the end, right? So what these degrees of freedom would basically tell you how much you need to slow down or accelerate your motions to ensure that the system will stay at the same temperature. This will be the Nose-Hoover thermostat, and we will derive it next time. The next step will be the Barrowstat thermostat. Now, the algorithm for doing that, the most commonly adopted, is the Raman-Barrowstat algorithm, which is essentially the same idea, but now what you want to do is not only rescale time, but also rescale space, so that you adjust the size of the volume. So you basically act on space-time itself to ensure thermodynamics, if you want to make it sound very catchy. Okay? Now, while the derivation of the Barrowstat thermostat is in the notes, I will not ask for it because it's a little bit more complex. It requires you to remember what the virial theorem is, and then you will need to go through a little bit of complicated math, which we could do, but then we wouldn't do other things. We will focus on the Nose-Hoover thermostat theory in this course. But the global principle underneath both of them is the same. And as we shall see, this is very different from alternative methods that are based on stochastic dynamics, which is the next chapter of our course, after we will set up the exercises you will have to do. Okay? But there is one thing, and this is the last thing I want to stress, and you have to keep this very clear in your mind. The moment you keep temperature fixed, for example, by this trick, the dynamics Now, you might get the right thermodynamics, but the dynamics is clearly not the same as the previous one, because your degrees of freedom will be coupled to these extra degrees of freedom. So, is it still true that molecular dynamics carries the full information about the dynamics of the system if I keep temperature fixed? Strictly speaking, no. So if I were to be extremely strict and say the only protein folding simulation I could possibly do is microcanonical, because that's the only thing that I have a solid ground foundation that starts from the Schrödinger equation to the equivalent Newton's equation, because we went all the way down from the Schrödinger equation, remember? And that, I mean, as long as your force field is a good parameterization of the Born-Oppenheimer, as long as there's a nested sequence of hypotheses you're doing one after the other, but each of which is well-grounded and in principle controllable. And then if you follow that chain, eventually you are bound to follow the dynamics of the system and the equilibration. Too bad you cannot do that. So what people really do is adopt one of these alternative strategies even for dynamics. And the underlying idea is we are coupling to 1 degree of freedom only introduces minor rescaling of velocity. The error we are making is probably within the error of the force fields and all the assumptions that we are making before. But it's a hope. It's not something we are granted from any controllable parameter. Now, why am I bringing this up? Because eventually when you compare theory to experiment, you have to have clear in your mind what is the set of approximations you're looking at. I'm not aware of any evidence. I'm not saying there isn't. I'm not aware of any clear evidence that this really completely destroys the dynamics. But there's no proof that it doesn't. Okay? It's reasonable that out of 1 million degrees of freedom, adding one that just adjusts the velocities doesn't really screw you up. Does it? Maybe not. You have to check with experiments. But since when you check with experiment, you check normally of collective R with large objects, you have so many things to worry that this is probably the last in your checklist, at least in this course, and at least for the next couple of decades, I would guess. And if you ever come to a point that we have to worry about this because everything else is under control, well, we've gone a long way from where we are now. Right? Okay, so tomorrow we will derive the Nose-Hoover thermostat. We will just mention the Raman-Parinello prorostat, and we will start thinking about the next move, which is set up the exercise you will have to do. Okay? Once we set up the exercise, we'll go on with theory. And the exercise and theory will always go in parallel. In other words, up to now, say up to tomorrow, we arrive to a point where you are equipped with information to start making a simulation, knowing what a simulation means. So you will make a simulation and generate some molecular configurations that arguably have some meaning. Next, we will face the problem of interpreting those simulations. So as our course will progress, we will face the problem of dimensional reduction, data interpretation, clustering, and blah, blah, blah. And you will do that to your set of simulations. And then towards the end, remember the title of this course has AI as a first word, or machine learning, and we haven't touched that yet because it's not the first thing you would do. Then there will be a last part of the course in which you will be assigned a task to report how ML can speed up and has been used to tackle each of the problems that we touched. Selection of the force field, the generation of trajectories, and the interpretation of trajectories. Okay? so that eventually this will create, hopefully, a coherent picture. Okay? Good. See you tomorrow.